As far as septic systems go and drain fields, that type of sand, that fine sand, is not good for drainage. So we're looking for a coarse sand. So it's almost going to look gravelly, so kind of real small pebbles mixed in with the sand. If you've ever seen that type of sand, that's perfect sand for drainage. That's ideally what we're looking for. Hey guys, welcome to episode 6 of Ask The Pumperdude. I appreciate you being here. We've got a really good question from one of our viewers. It's going to be real informative for anybody with a septic system. But first thing, I wanted to show off these shirts that we got. Anybody local in the Michigan area, we've got our Michigan Strong t-shirts, as we're all getting through the end of pandemic season and every other season we're going through. But local t-shirt company in Brighton, Michigan, Big Frog, reached out and trying to support small businesses. They're making t-shirts with logos on the back, and so just a cool little fundraiser for any small businesses that are trying to get through these times. So I'll put a link in the description for anybody who's interested. Support a local company, and then they give us a little bit of the cost of it back to us. So really cool, really nice shirts, and show our Michigan pride. So here's our question for today, and it comes from viewer Ben. So Ben, I appreciate your question. He wanted to have some more information into what makes up a drain field. What's the function of the drain field? What goes into the installation, and some of the requirements that we look at when installing a system. So there's a few things that I want to touch on that are important when it comes to drain fields. We're going to go over Perc Tests. We're going to talk about differences between concrete and plastic tanks. We're going to talk about conventional installations, as well as the differences and the reasons why you might have an engineered system. So there's that term gets thrown around a lot, engineered. We'll talk a little bit about what that actually means. And then we'll just touch a little bit on alternative systems. There are some different circumstances that call for I guess maybe kind of extreme different types of treatments that are used for the effluent that comes out of the septic tank. So anytime you're looking at either installing a new septic system or a replacement, the first thing that's going to need to be done is a Perc test. And what that is usually in coordination with your local health department. What we're looking at is the soil type in the ground. Each county, at least in Michigan, and it's different. Some states have a statewide sanitary code. So depending on where you're at, there may be a local county that has requirements, or some of them are statewide. But what we're looking at is typically between 12 to 15 feet deep in the ground. So what we need to find is a good sharp sand. And what that sand looks like, because there are different types of sand, and I can just had yesterday a customer, they have a sandy soil, but it's a fine sand, and what happens with that fine sand is it gets very compacted, and it's some of the worst soil that we deal with when we're trying to dig up septic tanks, because it gets hard as a rock. And when we're trying to probe, we've got a rod that we probe the ground to locate the tank and lay out and try to find the lids. when you're probing, when you pull the probe back out, that sand just fills in that hole. So you have a really hard time getting through the ground with a probe. So it makes it very difficult. But as far as septic systems go and drain fields, that type of sand, that fine sand, is not good for drainage because it gets compacted, and then at that point it doesn't allow the water to drain through it at a rate that it's acceptable for getting rid of the water that's coming out of the septic tank. So we're looking for a coarse sand. So it's almost going to look gravelly, so kind of real small pebbles mixed in with the sand. If you've ever seen that type of sand, that's perfect sand for drainage. That's ideally what we're looking for. And again, codes are going to vary throughout the country, but our local code calls for at least 4 feet of sand beneath the drain field. So the Perc test is going to involve a machine coming out, backhoe or an excavator, and we're going to start digging. And the inspector from the health department will be watching, and as we go down into the ground, we're going to see different layers of soil, because typically you're going to find topsoil at the surface. So you might find 6 to 12 inches of topsoil, and then you might get into some clay, and then once you get through that, once we hit that good coarse sand that we're looking for, then we're going to need to go down another 4 feet to make sure that there's an adequate amount of sand for that treatment below the septic system, and that there's going to be proper space for that water to drain away. And then we also want to make sure that there's no seasonal high water table in the area. So we'll get back to that when we get to the engineered systems, but the high water in the ground can cause a problem with conventional installations of the drain field. So again, we're looking for 2 things. We want to make sure that the drain field is not too deep in the ground. Most of the counties in our area call for no more than 24 to 30 inches of cover on top of the drain field. And the reason for that is we want it close enough to the surface so that it can get oxygen from the surface. We've talked a little bit before in some other videos about aerobic versus anaerobic bacteria. We want to get good aerobic bacteria growth in the drain field, and to allow that to happen, we want to make sure that we're getting oxygen from the surface so that bacteria can be in an aerobic state as opposed to an anaerobic state. So we want to be close enough to the surface with our drain field, hit that good coarse sand so we have good drainage, and have at least 4 feet of sand below it. So once the Perc test is done, that's really going to give the contractor the requirements that are needed to give a bid on the replacement or the original installation. We're going to know things like how much sand we need to bring in, because if let's say there's 5 feet of clay on the top, the top layer of soil, and then we hit that good 4 feet of sand below that, that clay on top has to be removed, and then we need to bring in more coarse sand so that we can get the insulation layer of the drain field close enough to the surface so we meet that requirement. So the Perc test will give us the requirements for how much trucking of material in and out that we're going to have, as well as size of the system, whether it's going to be a conventional or an engineered installation, and then any tank size requirements, and all of those items will be listed once the Perc test is done. And typically, once the Perc test is done, that's the first requirement in the permitting process. And once the Perc test is done, we can go ahead and give a bid. And once we know at that point that what the requirements are. So Perc test is done. The bid's been accepted. We're going to start the installation. The the first thing that we need to know, do we need to install any tanks? Obviously, with a new installation, new build, tanks are going to be set based on the size requirement of the house that's being built. So it's typically designed based on the number of bedrooms in the home. Our local county's base water use as 75 gallons per day per person that could occupy the home. And they typically size the system based on having 2 people per bedroom in the home. So if you have a 3-bedroom home, 2 people per bedroom, the entire system would be based on usage, the average usage of 6 people. So 4 bedrooms would have 8 people, 2 bedrooms would have 4 people. And so that's going to tell us what size the tanks need to be, as well as the size of the drain field. So new installation, definitely going to be adding tanks. If it's a replacement system, sometimes the existing septic tanks are going to be okay to continue to use. They may not need replacing. So what will happen is those tanks will need to be inspected, make sure that they meet the current size requirements for the current code, and as long as they're in good condition and they meet those requirements, they'll be able to be continued to use. If they don't pass inspection, or they don't meet the size requirements, they'll either be abandoned, or crush the tanks and either remove them or fill them, and or sometimes if they don't, if they're in good condition but don't meet the size requirement, we may be able to keep those in use and add a secondary tank beyond that, so that we bring the size requirement up to code. So there's a couple different variables there, but usually an existing tank will be able to be used again for the replacement system. Different types of tanks. So we quite often get the question and the assumption from homeowners that concrete tanks are no longer used, and now we use plastic because it's a newer technology. And that's not actually the case, at least in the areas that we work. Concrete tanks are the preferred tank to be used for an installation. The biggest reason for that is they're going to stay put. What we'll find with the plastic tanks, they're so light that when they are emptied, at the time of a septic tank cleaning, you can get this floating effect where they start to pop up out of the ground. And when that happens, any pipes that are connected to it are going to be disturbed and either break or come jarred loose, and that's going to be a huge issue. Me personally, I've not seen that happen very many times with plastic tanks, but it is a possibility. So you also with plastic tanks, they need to be anchored. So there's a little bit more to the installation rather than just dig the hole, set it in place. You've also got to anchor them as well. So typically plastic tanks are going to be used when it has to be set in an area where the tank truck can't get to. Maybe on the side of a hill if it's a really sloped property, or it's there's just not a possibility of putting it in the front yard and it's such a tight lot that you can't get the tank truck around the back of the house to set the tank. So the plastic tank can be more easily moved into that area and set. So that's typically the only time you're going to see a plastic tank, is when you just can't, for whatever reason, you can't get the tank truck into the area to set a concrete tank. So most tanks we're going to see are going to be concrete. I would say probably at least 99% of the tanks that we see on a daily basis when we're out cleaning are going to be concrete. So let's talk about a conventional installation of a drain field. Um, the majority of installations are going to be of the conventional variety. There's some variables. There's a little bit of differences, but they're all basically the same. You're going to have the septic tank. All the plumbing from the house is going to drain into the septic tank. There's going to be a pipe coming out of the septic tank that leads out to the drain field area. The drain field is a series of pipe in the ground, all connected together. That pipe has holes in it, typically on a 45-degree angle, and that those holes allow the water from the septic tank to drain into a bed of stone. And typically in our area, we're going to have 12 inches of stone. And we sometimes hear people talk about, they may have installed their own system and may not have gone through the permitting process, and we hear that they use pea gravel or they used real large stone. The type of stone that's used for drain fields is 6A. So that is the size of the stone, and the stone's going to be about this size here. And the reason that we use that size stone, we want a little bit larger stone. So pea gravel is going to be too small. It doesn't create enough surface area to allow a good growth of bacteria, which we're not going to get a appropriate amount of bacterial action in the drain field to clean that water before it gets back into the ground. So we want a little bit larger stone so we have that surface area. The we can get enough bacteria in there that can handle cleaning of the water that comes out of the septic tank. But we don't want too large of a stone. If we have too large of a stone, we're going to get these bigger gaps in between the stones. So if, say we've got stones that are this size, they're going to be in here this way and then this way, and we're going to have all these large gaps in there where the water's going to get through the stone too fast. We may have a lot of surface area for bacterial growth, but the water may not be hitting all of the stone, or it's going to be coming through too fast where it's not getting the particles cleaned out of it before it gets through the drain field. So 6A, that's the size of the stone that's used in drain fields. Let's talk about how the pipe is constructed. So we've got the septic tank. The pipe from the septic tank is going to come downhill to the drain field, and it's going to come into a header. There's a couple different types of headers. The simple header is just going to come, the pipe's going to come downhill. It's going to come into a T that splits it this way, and then there will be lines that come off of that header. Most of the time between 4 to 8 lines, and those will all be connected together at the back with a footer. So they're all going to tee into another pipe at the other end of the drain field. So the goal of the system is that the water comes out of the septic tank, comes down that line, hits a T, causes that water to spread out sideways through the header, and then push down those lines equally. So ideally this should all be level. The water is going to spread out evenly throughout the entire drain field and drain out of those holes in the bottom of the pipes and get equal distribution through the entire drain field. The reason we want that is to make sure that the entire drain field is getting used, which will allow it to last as long as possible. If all of that effluent comes out of the septic tank, pours into one side of the drain field, and only uses a couple of the lines, we're only going to be using 20 to 40% of the drain field, and it's just not going. Those lines won't take the water as long as it won't last as long as if we're spreading that water out throughout the entire system. So that's the basic construction of a conventional system. Pretty simple. The only other variation you might get sometimes is the use of a bridle header, and what that's going to be, it's kind of a mini header before you get into the main header of the drain field. So the drain field will be constructed the same way. We've got the header with the lines coming off of it. With the bridle header, you've got the line coming from the septic tank. It's going to come into a mini bridle header, which is going to divert the water to two sides of the drain field. So that bridle header is going to tie into 2 points of the header, and it just guarantees more, better distribution, to making sure that even if that header wasn't perfectly laid level, it's forcing the water to get to both sides and give an even better chance of proper distribution through the entire drain field. One other variation that we're going to see, the drain field that I've been describing would be a bed construction. So it's the entire area of the drain field is filled with stone, and with the pipe running through it. Trench system would be another variety of a conventional drain field, and it works the same way. You're going to have septic tank draining into a header that's diverting the water. We got lines coming off the header, but instead of having stone throughout the entire area of the drain field, we're only going to have trenches where the pipes are laying. So typically those trenches will be 2 to 3 feet wide, and there will be stone laid only in the trench. So you'll have one trench with stone in it, you'll have an area that's undisturbed, and then another trench with stone and pipe through it, and so on throughout the entire drain field. We don't see a huge difference in longevity between a trench system and a bed system. Typically, permits are going to be written for a certain square footage of stone in the drain field. And so a trench system may take up a little bit larger area than a bed system does. So the bed system can be a little bit more compact because you don't have those kind of blank spaces throughout the area of the drain field. But everything else is working exactly the same way in either one of those systems. So that's the basic rundown of the conventional system. I don't think I mentioned it yet. We've mentioned it in previous episodes, but throughout that stone in the drain field, we're going to get a naturally occurring layer called a biomat, and that's where the majority of the bacteria is going to be present in the stone of the drain field. And again, that bacteria is there to remove the particles that are in the water that come out of the septic tank. And so that by the time the water drains through that stone in the drain field and gets back into the ground, it's a good clean water again. It's not going to contaminate it. It's not going to contaminate any waterways or drinking water below. So that's conventional. I'll touch a little bit on the engineered systems. We talked a little bit before about why we might need an engineered system. A lot of times it's usually going to be one of two things. Either that you're going to have a high water table in the area, so we don't have enough room to get that 4 feet of sand beneath the drain field before we hit the seasonal high water table. So we can't guarantee that water is going to be completely clean before it gets in there. The other reason would be poor soil type. those are going to be the two main ones. I don't want to get too complex. There are other variables that go into it: elevation differences, the distance between where the septic tank might be and where the drain field needs to be installed. If there's a very large piece of property, it could be, there's some systems where the drain field might be a quarter mile away from where the septic tank is, and you'll have a pump chamber installed that'll push the water all the way out there. But a lot of times it's just a matter that there's not enough room in the ground to get adequate drainage before we get back to the, so that water's clean before it gets back to the water table. So what will happen is we will find that during the perc test, there's not enough sand. We know that we've got to elevate the system. So maybe we do the perc test, we get 3 feet of sand, and then we hit water, hit the high water table mark. That means we're going to have to elevate that system a foot higher than we normally would. So that system might be coming a little bit up out of the ground. So you might see at your home or ones that you've driven by before where there's this mound. It's just a perfect kind of flat on the top, and then it tapers off on the sides. That's the typical look you're going to see with an engineered system. Almost 100% of the time with an engineered system, you're going to have a pump chamber involved. So you'll have a septic tank, maybe multiple septic tanks, and then after the last septic tank, you'll have a pump chamber. So this is another tank. It's got a pump in the bottom. So as water gets used in the house, that water pushes through the septic tanks into the pump chamber. As that pump chamber fills up, there's a float switch that turns on, tells the pump to kick on, and it'll pump the water out of the pump chamber to the drain field and allow it to drain into the drain field that way. And it pumps the water down, the float switch tells the pump to turn off, and it waits until enough water has been used in the house again to kick back on. So some of the common engineered systems that you're going to find, the most simple is going to be what's commonly referred to as a pump and dump. So what you have is you're going to have basically an identical drain field to what we described as in a conventional system. So this same setup with the header, the lines coming off of it, the footer, they're all tied together, a foot of stone underneath the pipe, and what's happening is that pump is going to pump it out, and it's going to push it into the system, and it's going to travel through those pipes the same way as it would in the conventional system, and drain through the stone back into the ground. So that's real simple. Same idea as a conventional system, but for whatever reason that system had to be elevated. So the drain field is higher than the septic tanks, and it had to be pumped up to it. So that's the pump and dump engineered system. Other systems are going to be a pressure system. So you're going to have smaller pipe in these systems. I'm not sure if I mentioned it, but a conventional system or that pump and dump engineered system is going to have 4-inch perforated pipe. So it's 4-inch pipe with the holes on both sides going out on a 45-degree angle on the bottom. The pressure system is usually going to have between 3/4 inch to 1.25 inch pipe. And this is out in the actual drain field in the stone. The pipe coming off the pump may be 1.5 inches to 2 inches, depending on the pump requirements. But so the pump's going to push that water out. There's going to be holes drilled in those smaller pipes that are in the stone, and they're usually set on a 45-degree angle. And it's all, each engineered system may have different requirements, but it's all spelled out in the engineering, which is obviously why it gets that name, engineered system. typically a sanitary engineer is going to design that system. So there's a little bit more of an expense with the design process of an engineered system, and it may take a little bit more time to get started on the installation, because there's that design has to be created before it can be installed. So, but the number of holes needed and the spacing will all be all that information will be in the blueprints for the engineering, and so what's really important about this type of system, a pressure system, is that you're always going to get perfect distribution through the system, because it's pressurized. When that pump kicks on, it's going to push water through, filling every single bit of pipe that's out in the drain field, because it's pushing water faster into the pipe than it can get out through those small holes that are drilled into those pipes. So it's completely pressurized, being a pressurized system, and so you get perfect distribution through the entire drain field. And that's the only way that you can really guarantee complete distribution and use of the entire system, is with a pressurized system. You should expect similar longevity between most engineered systems and conventional systems. A lot of times people think that maybe an engineered system is better. It has been engineered. It's a more specific system for what's needed on that property. And yeah, that's the case, but it doesn't necessarily mean it's better or it's going to last longer. It's actually kind of the opposite. You'd prefer not to have an engineered system. Number one, the cost is going to be significantly more. You've got more components. You're typically going to have more tanks. You got the pump chamber that's going to need to be installed. You've got the expense of the pump itself. The pump and its components they're mechanical items that they're going to go bad over time. You're going to be replacing pumps typically between every 5 to 10 years, and similar time frame for the float switches as well. So there's that expense that's going to be incurred over time with an engineered system. So it's not something that you want, but it's also not something that you should be overly concerned with. If you find that you're purchasing a home and it has an engineered system, you just want to make sure that it's inspected, that it passes inspection, and just know that those expenses should be expected over time. Every 5 to 10 years, you may be putting a pump in, and that can be in the $600 to $1,200 range to do a full replacement of the pump and the float switches. So something that you just definitely want to plan for if you have that type of system. Other systems that we'll encounter periodically are going to be some alternative systems, and these are a little bit more rare to find, and they're not as widely known about. And part of that reason is because there's always new technologies that are being developed with drainage systems, with these engineered septic systems, and they'll find that one idea didn't work so well, and it'll be phased out, and another one will come in. They'll start installing this other type of system, and these alternative systems, you maybe have heard of sand filters, pre-treatment systems, and aeration is also a lot of times involved with these alternative systems. They're just what they're trying to do is they're trying to find better ways of getting that water to drain in soil types that aren't not set up for proper drainage. So real heavy clay, real rocky type soil, or or that fine sand that we were talking about that just doesn't drain real well. What they're trying to do is get that water as clean as possible before it gets back into trying to drain into the ground. That's going to, number one, obviously just help that water go away, but it's also going to help with the longevity of the system. When we have soil that's having poor drainage, we're going to be susceptible for anaerobic bacteria growth, because anytime there's heavy water use from the house and there's a lot of water that comes out to the drain field, we're going to get this flooding effect where the drain field is holding water because it's not able to drain away as fast as it's coming in. And anytime that drain field is holding water, it's not getting oxygen from the surface. And when that bacteria gets suffocated, it's going to go from aerobic to anaerobic. And that anaerobic bacteria only works at about 70% the productivity of the aerobic bacteria. And what we'll find is that that's going to allow the biomat in the drain field, that bacterial layer, to thicken, and it becomes sludge-like, and it also starts to work against the drainage and won't allow the water to drain through like it should, and it's going to accelerate the rate of failure in the system. So these pre-treatment systems, whether it's a sand filter or there are some name brand systems. Aranco makes some, Advantex makes some. There's different brand pre-treatment systems that have filters. They have aeration, which is adding oxygen to help accelerate that aerobic bacterial growth. The sand filter is just like it sounds. It's a filter. It is making the water go through the sand to help filter it so that it's cleaner before it drains from the sand filter into the conventional drain field to help. Again, that cleaner water is going to drain away easier than if it is full of particles. And then the same thing with the pre-treatment systems. There's many different setups, but a lot of times the pre-treatment, it's basically a tank that the water comes into it. It's going to go through aeration, so there's constantly oxygen being generated into that effluent. The water is going to be pushed through filters, so it's got to go through this process before it can be sent out to the drain field. And again, allowing it to, giving the system a better chance for a long life, and be able to get that water to drain in soil that's not optimal for drainage. So a little bit more complicated on that end. A lot of those systems are going to have more complex control panels to control the pumps. There may be more than one pump involved in these systems. There's going to be timers that only allow so much water to be pumped out to the drain field at one time. So it'll be set up for a very specific number of gallons that are allowed to go out to the drain field, and then it has to rest for a certain period of time. And then once that time has passed, the timer will say, okay, you can go ahead and pump some more water out there. So it's giving it just small doses of water over, throughout a 24-hour period. So even when there's not active use in the house, it's still continuing to pump out a little bit at a time so that the drain field and the soil below it can keep up with the amount of water that's coming out and avoid that flooding effect. And then there's other combinations of float switches and like I said, multiple pumps and components in the control panel that are going to get more complex when it comes to diagnosing if there's an issue. Cost, again, replacement cost when there are issues. So you want to be informed on what type of system, and I'm talking about if you're looking at purchasing a home and you find out that it has one of these alternative systems, you want to really get an understanding of what is involved in taking care and maintaining that system, because that can become costly. Some of those pre-treatment systems will also require a yearly inspection. So there's another expense involved, along with just your regular cleaning of the tanks and any pump issues that may happen. You're also going to have an inspection cost on top of that that's going to add up over time. So just make sure you're getting all the information, not just did it pass or fail, what type of system is it, what type of maintenance is that system going to require, and what kind of costs does that involve. Just so you have an understanding when you go to put that offer on the house, that may affect the way that you're looking at the expenses that you're going to see in the future. So those are most the most common types of systems that we're going to see. I would say probably about 80% of the systems we see are going to be in the conventional variety, where we've got tank drains into a header diverts that water into the system, and it drains through the stone, cleans the water, and goes back into the ground. That's going to be by far the most common system that we see. Your engineered systems are going to be probably another, if there's 80% conventional, we're probably seeing 15 to 17% engineered systems, where we've got a pump chamber, and for a variety of reasons, the drain field's got to be elevated above the septic tanks, so it's got to be pumped up, and it could be just flowing out and spreading out in the drain field. It could be pressurized, where we get that real good distribution of water through the system. And then 3, 4, 5% of the systems that we see are going to have that pre-treatment alternative type of system, where we've got filters. Could be a sand filter, could be a different type of media filter, with that aeration and control of how much water is being allowed to exit to the drain field. Where you're going to see that system installed is typically where there's a less optimal type of soil in the ground for drainage. So I hope this answers some questions or shed some light on what you may have in your backyard, and what you want to be thinking about as far as maintaining that system and getting every bit of life out of it as you can before you have to go through that replacement process, which again starts with that Perc test, and go through the permitting process and find out exactly what's going to be required today. And that's another thing that's that you can run into. Don't always expect that what you have in the ground today is what will be required for replacement. The codes have changed significantly, and especially when you should be expecting somewhere between 20 to 40, sometimes 50 years in the life of a system. The sanitary code may be completely different now, so it's important to know that what's in the ground today may not be what you see someone bidding that job for a replacement. It may look different. It may you're definitely going to be looking at different size septic tanks and size of the system overall. So just some things to chew on. Hope it gives you a little bit better understanding of what a drain field is, what it takes to install it, and what you'll be looking at when that day comes that you need to replace. So thanks again, Ben. I appreciate the question, and keep the questions coming. That's the best way that I know what it is that you want answered. And I'm happy to do it. So I appreciate you guys tuning in, and we'll see you on the next one. Have a great day. Bye.